graphing rational functions. And the philosophy of how we'll graph rational functions will be a lot like how we graph polynomial functions. We will pick out. Is anyone lacking last time's notes? Anyone else lacking last time's notes? Cool. Let's see. I think I remember a hand being up here. And here. And here. Yeah, that'll do. Nice. Did I miss anyone whose hand went up and I just ignored them? Okay. So let's think about how to graph rational functions. And here's the philosophy. I'll pick out the details that I want. Let's make sure that our graph has the correct intercepts, the correct asymptotes, and is positive and negative the correct ones. That's about all you can expect from a cartoonish hand-drawn graph. So let's try to achieve that. And if we want those details, let's find those details. So there's the thing that needs to be graphed. Let's start by finding the x. Well, the y-intercept's the easiest one. Let's find the y-intercept. How do you find the y-intercept of a function?
X equals 0?
Yeah, you just plug in x equals 0. Yeah, sorry. You can shout things out today. I think my brain will be mostly off. Today's been a day. So plug in x equals 0. What do you get? You'll get 0 plus 1, 0 plus 2. Nope. 0 minus 2. All over 0 plus 2, 0 minus 1. So let's see, that's 2, 1 times negative 2. All over 2 times negative 1. Is that 1? I think that's 1. So that tells me the y-intercept, when x is equal to 0, I get a y value of 1. So this graph will definitely pass through the point 0, 1. So far, so good? How do you find the x-intercepts of a rational function? You figure out when y equals 0, and then you solve for x. And the only way that you can get a fraction to be 0 is if the numerator is 0. So I'll jump straight to the numerator. And see what we get. That's a super easy equation to solve, right? It's pre-factored. There's no need to FOIL it out. That'll just make things worse. What are the solutions?
-2 and 1.
Isn't it negative 1 and 2?
Yeah.
OK. So x plus 1 is equal to 0 will give us x equals negative 1.
Oh, yeah. I was looking at that.
Ah, OK, good. Keep those in mind, because those will be important in a moment. So there's 1 at x equal to negative 1, and there's an x-intercept at x equal to 2. Now think about the vertical asymptotes. To find vertical asymptotes, set the denominator equal to 0. Sorry, I'm going off screen. Again, that's super easy to solve in that you already solved it. Looks like x equals negative 2. Or x equals 1. So I'll draw a vertical line at x equal to negative 2 to encode that vertical asymptote. I'll draw a vertical line at x equals 1 to encode that vertical asymptote. Progress is being made. Where is the horizontal asymptote of this function? How do you find the horizontal asymptote? I guess we'll remember 2 different ways. Let's think of it this way first. So let's imagine we plug in x equal to like 1,000,000. So imagine a really, really big number for x. If I plug in like 1,000,000 for x, does that +1 make a difference? Does that -2 make a difference? No, so when x is really, really big, the numerator is basically just x squared. When x is really, really big, what can you tell me about the denominator? Also pretty much just x squared. So asymptotically, we have x squared over x squared, which is equal to 1. So there's a horizontal asymptote of 1. The other philosophy is if you actually read the theorem that we got out of that idea, well, there are 3 cases. One of them is when the numerator and denominator are the same degree. Is the numerator and denominator the same degree for this rational function? Yeah, they're both degree 2. So I just need their leading coefficients. If you FOIL out the numerator, what's the leading coefficient you get? 1. Right, you would wind up with an x squared and some lower order terms. Same thing in the bottom. You'd see leading coefficient of numerator divided by leading coefficient of denominator, which is 1 over 1, which is 1. Either way, y-intercept at y equals 1. Nope. Horizontal asymptote at y equals 1. So I have those details. Let's just make sure that the graph we generate has the correct positivity, negativity, and has those properties. So to the right of that vertical asymptote at -2, it will either always be positive or always be negative. Those are its only choices. How can we decide which? Well, there are 2 good answers. One of them is just pick a sample value. What's the sample value that is to the left of -2? -3. Using -3, I won't, because that's like the more computationally expensive way. I'll use the strategy that will let me skip all the computations. If I plug in x equal to -10 trillion, what will the y value be very close to? Where's the horizontal asymptote? 1. So the x values need to be very, very close to 1. An x value, y value very close to 1, will that be positive or negative? If a number is close to 1, so it's like 0.999999999, is that positive or negative?
Positive.
Positive. So by doing that, I don't need to plug in any numbers. I know that it will be positive because it's close to this asymptote. And it has no opportunity to become negative, so it has to get to the vertical asymptote at +infinity. That makes sense? That seem okay? We also could have plugged in x equals 3 in the time that it took me to say all that. So for the next step, I need to figure out whether it's positive or negative between -2 and -1. All right, so I guess now I have to plug in an x value that's between -2 and -1. Can you think of an x value between -2 and -1?
0.
No?
Wait, no. Sorry.
-1.5 would do the trick. So let's do that, and let's remember, I don't care what the output is. I just care if the output is positive or negative. So I'll be super sloppy. So let's see what happens when we plug in x equal to -1.5. I'll get a y value of -1.5 plus 1 times -1.5 minus 2 all over -1.5 plus 2 times -1.5 minus 1. Yeah, there's enough space for me to do it this way. So I only care whether this number is positive or negative. So just tell me about each factor. Is that quantity inside of parentheses right there positive or negative? 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 So I'll write something which maybe you wouldn't even, right? So let's see, it was negative times a negative divided by a positive times a negative. Is that end result positive or negative?
Negative.
Can you skip the sheet over?
Oh, yeah, sorry. So that means for all of the x values between -2 and -1, the y value will be negative. So to get to this vertical asymptote, the vertical asymptote has to then be at -infinity, because it has to be negative. It's going to get up to that x-intercept. So far, so good? So next, I guess we have to go from x equals -1 to x equals +1. What's an x value between -1 and +1?
0.
0 walks down. But we've already plugged in 0. What did we get for y when x was 0? 1. So we don't have to do any more work. We know it has to be positive. Whoosh. That seemed pretty okay? Next, between x equals 1 and x equals 2, it's either always positive or always negative. What's the sample point we could use? 1.5, that'll do. When you plug in x equals 1.5, do you get something positive or negative? Am I here a positive? Does that agree? Wait, positive? Did you say positive?
Yeah. Negative.
I want it to be negative, but I didn't actually do the walk.
Yeah.
Oh. Okay. I appreciate that honesty. Let's try to plug in x equals 1.5. So the other philosophy is like the thing that causes that vertical asymptote is an x minus 1 in the denominator to the power 1. And I know that that will switch from positive to negative, or negative to positive. So the whole thing should switch sign. So I think philosophically it should change sign. Let's do a quick check. Plug in x equals 1.5. We'll get 1.5 plus 1, 1.5 minus 2. So positive, negative, divided by 1.5 plus 2, positive, 1.5 minus 1, positive. How many times did I say negative? Just once? That's an odd number of times. So the whole thing should be negative. Okay. The whole thing will be negative. So that means that this vertical asymptote on this side, it should be going to -infinity. Needs to make it up to that x-intercept. And now maybe even without plugging in anything, if you take an x value that's bigger than 2, will the y value be positive or negative? Positive. And I guess there are two ways to think about it. It has to get close to the horizontal asymptote. Horizontal asymptote's at 1, so it has to be positive. I guess you could also plug in 3 and just check that all of those terms are positive. How do people feel about that? That seem okay? So let's go ahead and also notice, does the graph cross its horizontal asymptote? Yeah, and it had to accomplish even the right y-intercept, because the y-intercept was at the asymptote. Groovy. So I think I want to go through just the other example of graphing that's in this packet, and then we'll talk about inequalities. The inequalities packet is pretty short, so we'll be okay for time. But maybe I'll let you guys see. Do people want to see another example of graphing a rational function? Okay, cool. We will do one more example. The outline of steps will be the same. We will find the x and y intercepts. We will find the vertical asymptotes. We'll find the horizontal asymptotes. We'll check for positivity or negativity. And maybe I'll start by just like writing out the thing. So I need to find the y-intercepts, the y-intercept. There will always only be one y-intercept, at most. I need to find the x-intercepts. I need to find the vertical asymptotes and the horizontal asymptotes. And I want to avoid doing walk if I can. Where's the y-intercept? 3 halves. That agree? Does it actually agree? Where's the y-intercept? So I thought a negative 3 halves. Do I hear a different number?
Positive.
Positive 3 halves. Right, negative divided by a negative is positive? Yeah. Do people want me to talk through that? Okay. Seeing no heads nodding, we're happy. So y equals 3 halves, or if you like, 1.5. So I don't know if there's 1, 2. There's that y-intercept. All right, x-intercepts. Where are the x-intercepts of this function? X equals 1, x equals negative 3. Does that agree? Anyone want me to talk through those? Cool, then I'll draw them in. There's x equals 1.
Should there be a 0? Like, should there be 1 at 0?
An x-intercept at x equals 0, you mean?
Yeah.
Well, let's even just check that. Oh, so I know there can't be because that would violate the vertical line test.
Okay.
So if the y-intercept isn't 0, there can't be an x-intercept at x equals 0.
Okay.
And I've already started misdrawing. This is an x-intercept. You don't draw those as vertical lines. It's an intercept. So I'm going to switch to black for my graph. Then 1, 2, negative 3. There will be an x-intercept there also. Cool.
Does nothing happen to the 2 in front of the x negative, x minus 1?
Something will happen. But notice, so if you have something you just multiplied it by 2, the only thing you can multiply by 2 to get 0 is 0.
Okay.
Well, 2 is never 0, so it can't add any x-intercepts. Let's find the vertical asymptotes. The 2 will be relevant for horizontal asymptotes. Where are the vertical asymptotes of this function? Negative 2 and positive 2? So let's draw those. One of them at x equal to negative 2. One of them at x equal to positive 2. And now horizontal asymptotes. And maybe I'll talk through this one in full detail. So if you wanted to get the horizontal asymptotes, maybe I'll even FOIL the thing out. It's small enough. You'll wind up in the numerator with 2 times x squared minus x plus 3x minus 3 all over x. Yep. All over x squared minus 4. Continuing to distribute, 2x squared plus 4x minus 6 divided by x squared minus 4. So that's what you get if you just rewrite this, do some algebra to this rational function. What's the degree of the numerator?
X squared.
What's the degree of the denominator?
2.
2. So they both have the same degree. So I just need to take a look at the leading coefficients. What's the leading coefficient in the numerator?
2.
Leading coefficient in the denominator?
1.
1. So where's the y-intercept?
2.
That's right. Those are the only terms you need to look at for horizontal asymptotes. So the horizontal asymptote will be at y equals 2. All right. And so now the only place where this function can change from positive to negative or negative to positive is here, 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 and here. Those are the only places. So that means I can start by trying to see what happens for an x value that is more negative than negative 3. What is an x value to the left of negative 3?
Negative 4.
Negative 4 will do. Those of you who would rather plug in x equal to negative 4,000, feel free. So if I plug in x equals negative 4, I'll get 2 times negative 4 minus 1, negative 4 plus 3, negative 4 plus 2, negative 4 minus 2. And I don't care exactly what that number is. I don't really care about x equal to negative 4. I just care if it's positive or negative. Is that positive or negative?
Can you move it up?
Thank you. So you plugged in x equal to negative 4. So that's 2 times a negative number times a negative number times a divided by a negative number times a negative number. So it's positive divided by positive is positive. I don't care what positive number it is. So that means for all x values to the left of negative 2, this function is positive and it needs to get close to that horizontal asymptote. I could have also avoided that computation entirely, right? I knew that I had to get close to that horizontal asymptote, so it had to be positive. Nice. So next, I need an input between negative 3 and negative 2. What is such an input? Negative 2.5 will do the job. Plug in x equals negative 2.5. Do you get something positive or negative? Negative. Negative? Does that agree? Does anyone want me to go through the wall? Okay. So you told me it was negative, so it'll have to stay negative. So it will become negative, and I have to get to this vertical asymptote. Whoosh. From negative 2, the next place the y value can change sign is 1. What is an x value between negative 2 and positive 1?
0.
0. We've already plugged in x equals 0, though. What did we get?
3n.
3 over 2. In particular, it's positive, but we can draw that. So it'll have to go whoosh, get down to this y-intercept, and then continue down to get to the x-intercept. What is an x value? What's a good next x value to try to plug in?
1.5.
1.5 would do the trick. I need something between 1 and 2. Plug in something between 1 and 2. Do you get something positive or negative? Negative. So it will become negative and get to that vertical asymptote. Whoosh. Then it has to get to this horizontal asymptote, so it better do something like that. Oh, yeah, sorry. Wonderful. So the graph I get looks a little something like that. Does that agree? And let's just go ahead and notice again. Does the graph cross its horizontal asymptote?
Yep.
As we've seen, sometimes they just have to. There's no guarantee that it will. Yeah.
How'd you get the bit in the top right corner?
Top right. Okay, cool. Where is the horizontal asymptote for this function?
3 halves. Right now. Sorry, 2.
2. So that means for an extremely big y value, y has to be close to 2. In particular, if a number is close to 2, could that number possibly be negative? It has to be very close to 2. When I plug in a really, really big number, it has to be positive. But it has no opportunity to switch to being negative this whole time. So it has to stay positive, and it has to get to this vertical asymptote. Well, it can't go to negative infinity because it would have to become negative. So the thing will have to go up to positive infinity. Does that help? Otherwise, I could have plugged in x equals 3, I guess would do. And when you plug in x equals 3, you probably get something positive. You better anyway. Cool. Any questions about graphing? And hopefully this all felt pretty familiar from graphing polynomial equations. So the thing I want to introduce today is the idea of solving rational inequalities. And I'm going to go ahead and make one change to that first example. I'm going to switch it to a loose inequality from a strict. because other bits in the notes have that being a loose inequality instead of a strict. So I'll switch that to equated variable. Does anyone not have this note? Okay, Paul. We're good. So let's try to solve this inequality. And let's try to use the strategy that we've used in the past. If you want to solve an inequality, a good place to begin is by trying to solve equality. And as a remark, there is a fatal flaw in the plan that I'm about to make. I want to emphasize what that error is by making it. So let's follow through this. Let's start by solving equality. Let's figure out when x plus 1 over x minus 1 is exactly equal to 2. And, well, I guess let's just go through the walk of solving it. I see a fraction set equal to 2. It's annoying that there's a fraction involving x. So how can I make there not be a fraction involving x? Cross multiply, I think is the word. Multiply both sides by the denominator. So what do you get? You'll get x plus 1 is equal to 2 times x minus 1 is equal to 2x minus 2. So I see x plus 1 is equal to 2x minus 2. Is that now a simpler equation to solve? Would you even go so far as calling it a simple equation to solve? Okay, so maybe there's like a step. So I guess now you would want to, I don't know, subtract the x to the other side, add the 2 to the other side. So you'd wind up with 3 equals x. That feel okay? Right, that. Does anyone want me to explain any of those steps in more detail? Because I will. Okay. So we found a solution to equality. And you know what? I feel unconfident with myself because I'm convinced that I'm in a mindset where I will easily make an arithmetic mistake. So I'm going to plug in x equals 3 and just double check it. I'll plug in x equals 3. I'll get 3 plus 1 is 4 divided by 3 minus 1. It's 4 over 2. Yeah, that's 2. It checks out. OK, so I'm happy. So we've just solved equality. Let's put that on the number line right here. So there is x equals 3. That's the place where equality happens. So now that we've found a place where equality happens, we'll play this game where we check a number to the right of 3 and to the left of 3 and see what happens. What is a number that is to the right of 3? Oh. Let's see what happens when we plug in x equals 4. So I'll get 4 plus 1 over 4 minus 1. I am wondering if that is bigger than or equal to 2. I put the question right there because I know that I'm not saying that it is true. I want to know if it is true. And, well, let's see. So that means I want to know if 5 over 3, is that bigger than or equal to 2? Is it? Why not?
Because 2 is like 6 over 3.
Cool. There were a great many answers that I would have been very happy with. One of them was 5 over 3 is 1.6 repeating, but that's 1 point something, so it's less than. Another one would have been multiply the 3 over. Anyway, we get that that is false. So that means any x value bigger than 3 fails to satisfy. Nice. So now I guess I need one on the other side. What is an x value that is to the left of 3? 2. I also want 0. So those of you who say 0, plug in 0. Do it. And I'll plug in 2, and we'll notice something upsetting. So I'll plug in 2. And let's see what happens. It looks like I get 2 plus 1 over 2 minus 1. That's 3. Is that bigger than 2? So what that seems to suggest is that all of these numbers solve the inequality. Those of you who plugged in 0, did you get something that solves the inequality? That's bad. Because that means that the conclusion that I just made, you know it's wrong. So, well, I didn't leave myself space for this observation, but I'll write it anyway. Problem. X equals 0 will give, well, I guess 0 plus 1 over 0 minus 1 is minus 1 is less than 2.
Can you move it over?
Yeah. So problem is when we plug in x equals 0, we get negative 1, which is strictly less than 2. This does not satisfy the inequality that we want. So there's x equals 0. Something bad happened there. Okay, so that means that the strategy that we've used to solve inequalities will not work without adjustment in the setting of rational functions. And let's look at a graph, and that will tell us why. Well, it'll tell us, one, what the solution actually is. Right? If you can sketch a graph, you can solve inequalities. And it'll also tell us how to fix it. So let's try to sketch a graph of this function and see what we can see. So let's just do it. Where's the y-intercept?
-1.
-1. Where is the x-intercept? I think the x-intercept's also at -1. Okay. Where is a vertical asymptote? Where is a horizontal asymptote? And I know one other detail about this function. I know that x equals 3 should correspond to y equals 2. So there's 1, 2, 3, 1, 2. I know that the graph should go through that point. Right, we checked that, so we may as well have that on the graph. And that's enough to sketch a cartoon graph, I think. I need to get from the horizontal asymptote to the x-intercept, to the y-intercept, to the vertical asymptote to this point at 3, 2, and then on. So there's the graph of the function. And I want to know when this function is bigger than or equal to 2. So maybe I'll add to this. There's the line at y equals 2. So by looking at this graph, well, maybe I'll just give you x values, and you'll tell me if they solve the inequality. Do these x values solve the inequality? No, because I want y values that are greater than or equal to 2. So those are bad, those are bad. What about this y value? Does it solve the inequality? Is the y value over this point bigger than or equal to 2? Yeah, it's like way up there. So the solution seems to start at 1 and go all the way until 2, and then it stops solving. So it sure looks like there's the solution. There are the places where the y values are bigger than or equal to 2. And let's just say what interval that is. That looks like it's an interval from -1 to 2. And let's be careful with endpoints. Does x equals -1 solve the inequality? No. Why not? Is -1 even in the domain? When we plug in x equals -1, we divide by 0. So it can't, so we have to exclude it. Does x equals 2 solve the inequality? It does, so we should include it. There's the solution to this inequality, which we just read off from the graph. Yeah.
Is that supposed to be a positive one?
Yeah. I mean, it clearly isn't supposed to be a positive one. I clearly drew a negative sign. But I was wrong.
Would the
Yeah.
2 be a 3?
Yes. Yeah. Okay. But that means you understand better than I do at this point. So let's, with the remaining time, what I would like to do is say what the actual strategy is. Right? Oftentimes you'll want to not have to go through the walk of sketching a graph to solve an inequality. Let's just notice that it looks like particle asymptotes can foil us. They can cause problems. So we just need to take into account particle asymptotes. Here is the algorithm to solve an inequality involving rational functions. Step 1, find the places where equality happens, because those will be some of the places where inequalities can change. At a particle asymptote, as we just saw, bad things can happen. The inequality might change from true to false or false to true. So we need to find particle asymptotes. All right, those are places where the denominator, the bottom of the fraction, is equal to 0. Step 2 is the same as step 2 always has been. We'll play this game where we check some sample points between and beyond. And then, well, we'll write down the solution. As a remark, if you want to solve an inequality, should the x value where a particle asymptote lives ever be included? No. Because an x-intercept corresponds to you divided by 0. But you don't want to actually divide by 0. Division by 0 is something you cannot do. Places where you would divide by 0 have to be excluded. Places where there are particle asymptotes will always be excluded. Nice. Well, with those things out of the way, let's go through and resolve the inequality that we just solved by following the algorithm. So we ought to solve x plus 1 divided by x minus 1 bigger than or equal to 2. Step 1, solve equality. We did that on the previous page. What was the solution to equality? 3. Step 1b is find the particle asymptotes. Where are the particle asymptotes in this function? So there's x equals 1, which maybe I'll even advertise is a particle asymptote. There's x equals 3. That's a place where you saw equality. Now we'll play this game when we check some sample points. On the previous page, what sample point did we pick that was bigger than 3? 4. When you plug in x equals 4, do you solve the inequality or fail to solve the inequality? Fail. And I don't want to rewrite that. Maybe I'll just go ahead and write this. X equals 4. You fail to fails to satisfy the inequality. So that means all of these x values fail. What is an x value that is between 1 and 3? 2. And we plugged in 2 on the previous page also, I think. When we plugged in 2, what happened? Did the inequality become true or false?
True.
So this satisfies the inequality. Satisfies inequality. So that means all of these x values satisfy the inequality. What is an x value that is to the left of 1?
0.
0. We plugged in 0, happily, on the previous page. Or maybe I didn't, but you guys did. When we plugged in x equals 0, do we solve the inequality or fail? So that means all of these inputs fail to satisfy the inequality. So we see what the solution set is. It should be the interval from 1 to 3. There is a vertical asymptote at x equals 1, so should we include or exclude it? Exclude. We can't, 1 isn't even in the domain of consideration. You can't say that x equals 1 solves this inequality because you would be saying something that does not exist is bigger than or equal to 2. Should we include or exclude x equals 3? Include, because at x equals 3 we got equality, and equality makes us happy. That algorithm seem reasonable? Let's go through one more example of following this algorithm. Let's solve this inequality.
Can you move the paper?
Yes, thank you. X divided by x plus x divided by x squared minus 1 is less than or equal to 1 divided by x minus 2. So step 1, figure out when equality happens. I guess this is step 1a. All right, well, let's go ahead and solve that. I guess the first thing to notice is it's a fraction on both sides. That's annoying. In order to make it not be so fractiony on both sides, I'll cross multiply. So that'll give me x times x minus 2 is equal to x squared minus 1. That will become, just by distributing, x squared minus 2x is equal to x squared minus 1. Cool. What should I do next?
Subtract x squared minus, and then 1.
Yeah, I'll subtract that from both sides, so it'll cancel. That'll leave me with negative 2x is equal to negative 1. So what is x? Divide by negative 2. I think that'll leave me with 1/2. So x equals 1/2 is the solution to equality. So there's step 1a. Step 1b, find all of the vertical asymptotes of anything that happens. So what are the x values of the vertical asymptotes on the left or right hand side?
Plus or minus 1 and 2.
Coming from this piece, I see x equal to plus or minus 1. From this piece, I see x equals 2. Are people okay with that? Good. So that gives me almost everything. Let's draw this number line and pick some sample points. So x equals 1/2 is important. That's where equality happens. I know that x equals 1 is important. That's where a vertical asymptote lives. I know that x equals 2 is important. That's where another vertical asymptote lives. I know that x equals negative 1 is important, because that's where another vertical asymptote happens. Oh, yeah. Yeah. So I guess that means I have like 5 sample points I need to check. I need to check a sample point to the left of negative 1, between negative 1 1/2, between 1/2 and 1, between 1 and 2, and to the right of 2. Those are a bunch of computations that are all independent, so philosophically those should be done in parallel, and I will have you guys do exactly that. You guys look to the left of negative 1. You guys look between negative 1 and 1/2. You guys look between 1/2 and 1. You guys look between 1 and 2. I will do something for an x value bigger than 2. infinity, I got down to the inequality 3h is less than or equal to 1, which is true. So x equal to 3 has to be included, so everything to the right of 2 has to be included. And you guys did something similar. Let's just bring things together. Numbers to the left of -1, do they solve the inequality? What x value did you plug in? -2, and you got the inequality to be true. Is that what other people in that column got? Great. So those x values solve the inequality. An x value between -1 and 1/2. Did you get that it is true or false?
False.
False. Everyone's happy? X values between 1/2 and 1. Is the inequality true or false?
I got
True for something between 1/2 and 1? An x value between 1 and 2. False. And generally, at each of these points, usually something will change, but that's not universally true, so you do have to check. Now we'll decide about including or excluding endpoints. So it'll be negative infinity, which is always excluded, to -1. Should I include or exclude -1?
Exclude.
Exclude, because it's a vertical asymptote. Together with the interval from 1/2 to 1. Should 1/2 be included or excluded? Included, because 1/2 came from equality, and I want to solve an inequality that includes equality. Should 1 be included or excluded? And then it's the interval from 2 to infinity. Infinity is always excluded. Is 2 included or excluded?
Exclude.
Because it's a vertical asymptote. That algorithm seem reasonable? Nice. So, in addition to thinking about all of the other stuff that I've given you to think about, I collected homework, right?
No.
Okay, before you actually leave, would you mind either handing me the homework or putting it directly on this chair on your way out? Or else pushing me towards the middle. Thank you. The one that I didn't get to? I mean, yeah, then that I did it in the previous section.
Do the stapler this time?
Yeah. Oh, no, I didn't.
Yeah, go ahead.
Oh, no, we didn't actually finish it. I'll put one on there.
All right, thank you.
Yeah.